All right, y'all, so we're going to be talking about motion, forces, and Newton's laws, or the first and second ones anyways. And I've chosen this picture over here in the top right, not only because it's a little funny, but I think it also is a great analogy for how all of these things come together. And so if, let's say this little girl here who's clearly a little distressed, she's our forces, and I'm assuming that's her little brother. We call him motion. The get along shirt here are Newton's laws. And so Newton's laws tie forces and motion together, whether they like it or not, and tell us how they get along and how they connect and all of that. So we can use forces to tell us what's happening with the motion, and we can use motion to tell us what's happening with the forces. And oh hey, by the way, y'all, that is what Newton's laws are. They tell us these connections between forces and motions, and not only do they tell us what these connections are, but we can use the laws to get much more specific information. If we know stuff about the forces, then we can use that information to get all kinds of stuff about the motion. And the same goes in reverse. If we know stuff about the motion, we can use Newton's laws to give us all kind of specific stuff about what's going on with the forces. And so with our forces, we've got pushes and pulls, either through some mystical invisible rope that we call gravity, or from just somebody laying hands on a box and giving it their all. And so we get motion coming out of that, and we can get all into the details of both realms through the connection of Newton's laws. So forces, motion, we can really break each down into two categories. So with forces, what we have generally are, we've got forces that are unbalanced on an object, or forces that are balanced on an object. And then with motion, we have motion with it needs to be red. We have motion with a constant velocity, and then we have motion with a changing velocity. Now notice I didn't say moving or not moving, because in the realm of Newton's laws, not moving is not really a special state of motion. What the special states of motion are whether the velocity stays where it's at or whether the velocity changes. And so not moving is just a particular case of constant velocity. Not moving is a constant velocity of 0. The velocity is at 0 and it stays at 0. And that doesn't make it any more or less special than if the velocity was at 2 and stays at 2. So our special states of motion are changing velocity or constant velocity. And so what Newton's first law tells us are the connections between all of these things. So if the forces are unbalanced, Newton's first law tells us that the velocity of the object has to be changing, no matter what. And then if the forces are balanced, Newton's first law tells us that the velocity has to be constant. I also want to brag a little bit on my color coding, because I'm all about color coding. Notice here that we've got some blue action going on over here, and we've got some red action going on over here. And what happens when you put blue and red together? Oh my goodness, you get purple. So some deep metaphors going on there. But again, Newton's first law is about tying together one state of force with one state of motion. Unbalanced forces, changing velocity. Balanced forces, constant velocity. Bam, that's it. Newton's second law gives us much more detail about the kind of motion based on if the forces are unbalanced in particular. And so Newton's second law can help us answer these three questions here. So Newton's second law tells us the direction of the acceleration, or vice versa, the direction of the net force. Okay, And Newton's second law tells us that the direction of the acceleration and the direction of the net force are equal. So no matter what, 100% of the time, forever, ever, until always, the direction of the acceleration of an object and the direction of the F net on an object are exactly the same. Forever, always, forever. Okay? Newton's second law tells us not just the direction and not just that it is or isn't accelerating, but it also tells us exactly how much acceleration an object experiences. And so we get that from this handy-dandy equation where A, the acceleration, is equal to the net force divided by the mass. And so if we know the net force and the mass on an object, we divide them to get the acceleration. Or let's say that we know the mass and the acceleration of an object, we can then use this equation to solve for F net. And so that's, again, more of the links between if I know stuff about the motion, I can know stuff about the forces and vice versa, except Newton's second law allows us to do it quantitatively or numerically. We can get way into the weeds, okay? And then how much acceleration are we talking about exactly? Well, now that I think about it, I may have added that bullet point by mistake because that's exactly what we're doing right here. Well, you know, I'm reading my bullet points again, and this is what I get for not rehearsing my videos beforehand. What I have done here is I've answered this question right here, but I've not really answered what affects how much acceleration an object experiences. So I'm going to do a little switcheroo here, and we're going to talk about this down here. So if I look at the equation for acceleration equals F net over m, so net force divided by the mass, what this tells me is that the things that affect acceleration are going to be net force and mass. And we can really look at this as like an algebra problem, or we can look at it as a fraction, because that is what it is. We've got a numerator divided by a denominator. And so if we look at net force, it's the numerator. And so if we make this number bigger, so if we increase the net force on an object, while keeping the mass the same, my numerator gets bigger, and so my acceleration is going to get bigger. Okay. Now, if we do a little switcheroo, let's say we increase the mass. Okay, so we increase the denominator while keeping net force the same. Then if the denominator of my fraction gets bigger, the overall number is going to go down. So as my mass goes up, the acceleration goes down. And unlike most things in physics, this kind of makes intuitive sense. If you're trying to push on something with some amount of force and it's very large, has a lot of mass, your acceleration will not be that great. But if you put more force into that same object, you're going to accelerate it faster. So the harder you are able to push on it, the faster it accelerates. And again, we can look at this in reverse. If you're pushing your absolute hardest on an object and you're barely making it move, and then some jerkwad comes and pops another huge box on top of what you're trying to push, you may not even be able to push it anymore. Or at the very least, you're going to be pushing it a lot slower. Your acceleration goes down because your mass increased. So when you are looking at using Newton's first and second laws to solve problems, to figure out what's going on in a situation, you want to ask these questions all the time. Is the object speeding up, slowing down, or staying at the same velocity? What is the direction of the velocity? What is the direction of the acceleration? And are the forces balanced or unbalanced? And if they're unbalanced, what is the direction of the net force? So I'll quickly run through a few examples here of how to think about this. So if we look at a ball rolling down a frictionless ramp, Okay, is the object speeding up, slowing down, or staying the same velocity? Okay, intuition tells us that it is definitely speeding up as it rolls down that hill. What is the direction of the velocity? What is the direction of the acceleration? Well, the direction of velocity is usually pretty easy. What direction is it moving in? In this case, if I look at the picture, down and to the right. Now for the direction of the acceleration, I have to look at speeding up, slowing down, or the same velocity. Okay? It's speeding up, and so if an object is speeding up, that means the acceleration points in the same direction as the velocity. You can think of it as the acceleration is helping out the velocity. It's giving it a boost. Okay? Are the forces balanced or unbalanced? Well, the velocity is changing. In this case, specifically, it's speeding up. So the forces are unbalanced. And then the direction of the net force? Well, it's the direction of the acceleration. Already figured that out. Okay, let's look at a similar situation, but instead of this time, the ball is rolling up the ramp. Okay? So intuition again tells us that as the ball rolls up the ramp, unless it's being assisted, and it's not, it is slowing down. Okay? The ball is moving up the ramp, so velocity points up and to the left. Now here, the direction of the acceleration, we have to go back over here. So the object is slowing down, and so acceleration has to oppose the direction of the velocity. It's like chipping away at the velocity, tearing it down. And so we have to go opposite the direction of the velocity because it is slowing down. Well, the object's velocity is changing. Okay, it's slowing down. That is a change. So the forces are unbalanced. And then the direction of the net force is the direction of the acceleration, always, forever, 100% of the time. So just a quick recap. The idea here is that we use motion to figure out what's happening with the forces and vice versa. And the glue that holds motions and forces together, the get-along shirt that holds those two things together, are Newton's first and second law. Newton's first law specifically lets us make some general statements about balanced, unbalanced forces, constant, changing velocity. If we want to get into the weeds with numbers and exactly how the forces and acceleration and mass are all affecting one another, that's where we get into Newton's second law, where we use acceleration as equal to the net force divided by the mass. Now, what I didn't talk about here, and what you should do then, is check out some of my other videos. Am I pointing to the right part? Somewhere up there. Is that you can use this information in this video to as like a primer for interaction diagrams, free body diagrams, and vector addition diagrams. Because all of the information here helps you, set you up to draw these diagrams and actually analyze situations and actually start solving some physics problems. And this video arms you with the tools necessary to, well, use these other tools to solve these problems.